In the last video, we covered the parameters that define a Weibull distribution and their significance. Today, we will use them to calculate failure rates and for estimating the probability of failure within a certain time period. Let us assume that a bearing has beta value of 2 and the scale parameter is 4,000 hours. Since beta is greater than 1, the failure rate will increase with time. Also, as the shape parameter indicates, for this class of bearings, roughly 63% of the lot is expected to fail within 4,000 hours of operation. We would like to find out the failure rate for two time periods, 2,500 and 3,500 hours. Also, we will derive the average failure rate during this period. Finally, we will calculate the probability of failure of the bearing within 3,500 hours of operation. The formula for failure rate at time t is given on the slide. As we can see, this is a product of a constant and an expression which is a function of t. Since the power of t is positive, the failure rate goes up with time. By substituting the values of 2,500 and 3,500 in the expression, we can get the failure rates at those times. Since the failure rate changes over time, it is difficult to use this value for practical applications like inventory planning. This average failure rate is a value which is valid over a certain interval. Like in this case, we can derive it for the period between 2,500 hours and 3,500 hours. Using that, we can calculate the number of bearings that will fail during that period. The probability of failure is calculated using the function shown on the slide. Since t is in the denominator, the term on the right-hand side reduces with time, and therefore the probability of failure increases. We can directly calculate this in Excel, given time and failure rate using the Weibull.dist function. X here is the product of time and failure rate. Alpha is taken as 1, and beta is given. We use the cumulative form of the function. Okay, time now for today's assignment. It is similar to the problem we just solved, just that beta now is 0.67. A transistor has eta value of 5,000 hours. Find the failure rate at 500 hours and 1,500 hours, as well as the average failure rate between 500 and 1,500 hours. Also, calculate the probability that a transistor lasts beyond 2,500 hours. In this problem, it is clear that since beta is less than 1, the failure rate expression has a negative power of t. Therefore, the failure rate will reduce over time, and we can see that when we compare the rates for 500 and 1,500 hours. The average failure rate is 0.231 per 1,000 hours of operation. So if we were to start with 100, number of transistors expected to fail between 500 hours and 1,500 hours of operation would be 0.231 multiplied by 100, which is roughly equal to 23. This brings us to the last problem, and we have solved it both by using the formula directly as well as by using the Weibull function in Excel. The probability that it will last more than 2,500 hours is given by 100% minus 46.66% equals 53.34%. This is a very brief overview of failure rates and probability of failure for systems where the rate of failure changes with time. We will build on this when we get into more details on reliability in the upcoming videos.